last time we were discussing this topic, solar constant, and we said that is the maximum of radiation which is received from the sun at a particular instant on a unit surface area which is perpendicular to the direction of sun radiation. When the mean radiation, so uh, distance between sun and earth is assumed, then this value is around 1367 watts per meter square. But this value is not constant throughout because the sun earth distance is also not constant. That is also changing throughout the year. So because of this value also changes. So this is kind of an averaged value. Now some sources say that is 1367, it is about 1361 to be more precise. All right, but anyways, not a big difference. So here the solar constant. Starting from January up till December. So here is the variation between these two values, 20 and about 1420. So this is changing because the sun earth distance is also changing. Earth is nearest here is right. So this is a variation of about plus minus 3% from this average 1361 or 1367. And there is a to find out this solar radiation, solar constant as a function of day of the year. So this is one equation, this is another equation, this is a bit more, but this is also fine. Here you just put the value of n. This is the averaged value which we set 1367. So if we put any nth day of the year, we can find out the solar radiation, okay, for any day on the year. That is GSC, and that is the radiation on a plane normal, always normal to the radiation on any nth day of the year. Okay. So in this second equation, we see this term B, that B is given by this n minus 1 into 360 over 365, where n is the same nth day. Okay, so this is the maximum when the atmospheric effects are negligible. But once this around the earth, so then what happens? That is explained in the next slide. So the solar radiation, it gets because of various gases, because now this is, for example, the earth atmospheric boundary around the earth. So now we see there are many different gases in the atmosphere, dust particles, other types of suspended particles, there are water vapors, there are clouds, right? So that's why when the solar radiation, once it enters into the atmosphere, and while it is flowing through the or passing through that atmosphere, it gets some of it will be absorbed Some of it will be scattered, like this one, scattering. Some of it will be reflected back, right? Some of it will be reflected also due to the presence of all these gases, dust particles, clouds, etc. Right? So that's why the amount of radiation which will finally reach on the surface of the earth will be earth. It is of high temperature. The source is a very high temperature, and that's why as the temperature is higher, wavelength is normally smaller. So that's why we say the solar radiation is of short wavelength radiation. So the radiation which finally reaches on the surface of the earth, right, that is called terrestrial radiation. And that radiation which we said, which is the maximum one here, this is called extraterrestrial radiation or extraterrestrial region, where the effect of atmosphere is negligible. And this is the terrestrial region where this solar radiation gets absorbed, scattered, and reflected. And finally, the one which is reaches on the surface of the earth, it will consist of two parts, two main parts. One is the radiation which is directly reaching on the surface of the earth without being scattered or absorbed or reflected. That's called beam part of solar radiation. And the part which gets scattered uh, in different direction, it will also finally reach on the surface of the earth. Right, so that is called diffuse radiation. So we'll be discussing it again in coming slides. So the radiation which is finally absorbed by the surface of the earth, then earth will also start to emit radiation. But the earth average temperature is around 300 Kelvin. That's why the radiation emitted by the earth is long wavelength radiation, because the temperature is low. So if you see that Wien's displacement law, which we already discussed in the radiation part, so as the temperature rises, the wavelength at which the maximum radiation is emitted will be smaller. So here the earth radiation is, earth temperature is smaller, much smaller than sun. That's why the radiation emitted by the earth is of long wavelength. Sorry. Discussed this part, that is also explained here, which you can read by yourself, that scattered radiation, sometimes if it is scattered by molecules of different gases, it is called Rayleigh scattering. And if it is scattered due to small dust particles, then it is called me or my scattering. Okay, so some of it will be reflected as it is the short wavelength of that solar radiation. Some wavelength bands will be reflected back into the space because of different clouds, right? And there are different types of particles of large size and other materials which are there in the atmosphere. Okay, let's continue. Okay, so now here see the spectral distribution of solar radiation. So this green curve, this it represents a black body curve, black body at a temperature of this 5700 Kelvin, right? That is from the Planck's equation. We can obtain this curve. The the intensity of energy versus wavelength. That is the black body curve, and this green one. The red curve, this one. This represents the radiation, solar radiation, which is sphere on the top of atmosphere. this is the maximum radiation received, the solar radiation. So you can see that is very much similar to this black body curve. So our solar radiation um, is acting an ideal black body, but not exactly the black body, but the values are very near to the ideal black body curve. Okay, now finally you see the blue curve. So this blue curve, the solar radiation after it. So the blue curve is the radiation which is finally reaching on the surface of the Earth. Some of it will be absorbed. The absorption is at different wavelengths in water vapor, oxygen, or wavelengths. So that's why this blue curve is finally what we receive on the surface of the Earth. The ultraviolet part, which is less than 0.4 micrometer, that will be mainly absorbed in O3, right? This ozone layer that will absorb. The visible part, this portion is representing the visible part, 0.4 to 0.7 micrometer, that is least absorbed, and the peak transmission window, we can call it, right? So that's why solar spectrum peaks in a visible region, right? Similarly, near infrared, greater than 0.7 micrometer, that will be mainly absorbed by H2O and CO2 present in the atmosphere. So here the same thing is also explained here. Out of this total 100% incoming radiation, 30%, about 30%, sorry, about 3% is reflected, right? Due to these dust layers, air molecules, etc., water vapors, and lower dust layers. So this one is representing the reflected part or scattered space, right? About 3%. And the remaining, so all of this scattered or reflected does not go into the ambient or into the outer space, but about 7% is scattered towards the Earth. Okay, and this the part which gets absorbed is shown here, about 18%, that will be absorbed by the atmosphere, and the remaining about maximum about 70% on clear day, not every day, on a clear day maximum 70% could reach the surface, both now the direct radiation, which was not affected by the atmosphere, and this is representing the indirect radiation, or this is also called diffuse radiation. So this is the part which is finally reaching on the surface of the Earth. Yeah. So this is the top of the atmosphere, top of atmosphere, and this is the part which is finally reaching on the surface of the Earth. So our solar thermal systems consisting of PV cells or solar thermal collectors or of any type. So their efficiency will of course depend upon the amount of radiation which is finally reaching on the surface of the Earth, right? For this direct part, there is another term which is called DNI, direct normal incidence, right? And there is this term top of atmosphere. So this 1367, always remember this value and watts per meter square, we are talking about it, this part, top of atmosphere. Finally, which is reaching here, that is what we will see how to calculate or how to estimate this part, right, in this chapter. So that will be smaller than this 1367. All right. Okay, so let's move on. That's what I already explained. Okay, so here you see the three parts of radiation. The part which is finally reaching directly without getting affected is called direct or beam part. So here is the diffuse part due to the scattering within the atmosphere. So for example, this is the solar PV or solar thermal collector. This is our solar collector. Could be solar thermal collector or it's a solar PV cell. We normally mount it at certain angle. We will see how this angle is decided. We are using beta in this course for this surface tilt. So this surface is intercepting not only direct but also diffuse radiation, and also some part is reflected from the ground. This some part of this direct or diffuse radiation which strikes the ground surface and maybe finally gets reflected and incident on that solar collector. So the total amount of radiation which this solar collector or any other surface is intercepting consists of these three main parts, but the majority will be beam on clear day. Next will be diffuse and the reflected part from the surrounding surfaces. So that is explained here. You can read it by yourself. Okay. Okay. So I already explained what is direct or beam radiation, what is diffuse radiation. So if you sum them, these two, sum them, beam and diffuse, that is called global or total radiation. Sum of the diffuse and direct radiation on the surface of the Earth, that is called global radiation. The reflected radiation, the same short wave radiation, we are using the term short wave for solar radiation, as I already explained. So this short wave radiation, which is reflected from the other surfaces, that is called reflected radiation. And this plus this is called global or total radiation. Okay. Now there are different terms which we must remember during the course of this subject, that will be repeated at different times, and their meanings and their units must be clear. The first term which we normally use in solar thermal systems, that is called irradiance. Now what is irradiance? That is representing the rate at which radiant energy is incident on a surface per unit area. So this value of solar radiation, it could be global, it could be only diffuse, it could be only beam, it could be only reflected, or sum them all. So whenever the amount of radiation which is being incident with respect to time, so that is important. Here we are representing joules per second per meter square. So we use this term irradiance to represent that energy per unit time. Then there is a term which is called irradiation. It is joules per meter square. So if you integrate this irradiance over a times interval, over a certain time interval for 15 minutes or for 1 hour or for 1 day or even for 1 month or even for 1 year, if you integrate this term over a particular time period, then this is called irradiation. So irradiance becomes irradiation, and the units are now joules per meter square because we are multiplying with a particular time interval. Next is insolation. Insolation is another term to represent irradiation in the solar energy spectrum. So any radiation in the solar energy wavelength spectrum is also called insolation. We can use this term irradiance and irradiation not just for solar radiation, it can be used for any other type of radiation. But this term specifically is used only for solar irradiance or solar irradiation. So this is another term which is quite used in solar thermal system, insolation. Okay. Then there is a term which is called radiosity in radiation. This is the total radiant energy leaves a surface. For example, there is a surface. It is emitting radiation. It may be reflecting radiation. It may be transmitting radiation, right? Transmitted. So you already know the difference between these three: reflected, emitted, transmitted. So if you sum them all, then this is called radiosity, right? The total amount of radiation which is leaving a surface, not just by emission, also by reflection, and maybe if there is any transmission going on, if it is transparent material. So sum of all these is called radiosity. Then the another term which is used, that is called emissive power. It is only about this E, the emitted radiation by a body due to its temperature is called emissive power. Right? The radiant energy leaves a surface per unit area, watts per meter square, by emission only. Only the emission part is called emissive power. So try to remember all these terms. Those will be used to calculate different radiation, different type of radiation in coming chapters. Okay. So latitude and longitude, hopefully you already know. Latitude is used, or latitude and longitude both are used to specify any location on the surface of the Earth. So you very well know about this, so I will not take too much time. All these lines at the equator, the latitude is 0, approaching to 90 in the northern hemisphere, similarly 0 to minus 90 to 90 in the southern hemisphere. So these are representing the location of, of any point on the surface of the Earth in the north to south direction. That is north to south direction. So anywhere here we can use latitude to identify its location in the north to south. Similarly, to specify the location in the east to west direction, we have these longitudinal lines starting from 0 in Greenwich in UK, and then 0 to plus 180 on this side towards the east, and 0 to 180 on the western side. On the east side, we take it as positive, and on the western side, we take it as negative. All right. So any location on the surface of the Earth can be defined by defining a latitude angle and by defining the longitude that will specify the location on the surface of the Earth. Now, with all this background, which we have studied so far in this chapter, now on the basis of this, we will define some angles solar angles which are required to calculate the amount of solar radiation reaching on the surface of the Earth. All right, so let's go through those angles. So the solar angles, which define the Sun-Earth geometric relationship, those may be divided into two major categories. One is basic solar angles. The other are derived solar angles, which are derived from these basic solar angles. So what are these basic solar angles, which you can see here? Now we are visualizing the Earth. If an observer is somewhere in the space, here is sun radiations are reaching on the surface of the Earth. Earth axis is tilted. It is not rotating in along this axis, vertical axis. Actually, the Earth is rotating along this tilted axis, right? Which we called as declination angle or del. Right? So Earth tilt is always there. Okay. So now we can define different angles. The first one is latitude angle. So what was latitude angle? The angle between the lines joining this center of the Earth. So if you assume here is Sun, it is the center of the Earth, O dash. So this line joining the center of the Earth with the center um, of the Earth and center of the Sun, that is represented by O dash. Okay. Now this declination angle, sorry, latitude angle, we can define it as, uh, for example, here is the location P. So there is that line OP joining the center of the Earth with that location, and the projection of this OP on the equatorial plane, that is the equatorial plane. So if you draw its projection on equatorial plane, that will be OA, right? The projection of OP on equatorial plane is OA. So the angle between OP and OA is called latitude, right? And we are using this symbol phi, right, in this course. So whatever symbols we are using, so you try to memorize it because those will be required to use those equations to find out the available or absorbed solar radiation. So that is the first derived angle, which is called latitude. Okay, let's see the another angle, hour angle. So here it is shown, the hour angle. Now what is this hour angle? It is the angle between this projection OP, which we just discussed. The projection of OP is OA, right? So the angle between OA on the equatorial plane, that is the line OA, and the projection of the line OO dash. What was OO dash? OO dash is representing the line joining Earth center with Sun center, right? And its projection, this projection of O and O dash on the equatorial plane is OB. So this angle between OA and OB is called hour angle, and we are using this symbol omega to represent this hour angle. And you see, as the sun is rotating about its own axis, so this hour angle will be changing when this location is exactly in line with sun at noon. So at noon, you can expect this angle will be zero because there's this OB and OA, they will merge together at 12 noon. And as you move away in the morning and in the evening, this angle will start to change, right? So this omega is actually representing the um, angular displacement of the sun, right, with respect to east, because here we have east to west direction, because that is how it is rotating from east to west along north to south axis, about north to south axis. Okay, and this angle changes 15 degree in an hour. Okay. Anywhere on the location on the surface of the earth, this angle, or our angle, is changing about 15 degree in 1 hour. At noon, this angle will be 0, and in the morning, that is noon. In the morning, this angle will be negative. We will be taking this angle as negative. For example, at 12 o'clock noon, omega is 0. What about 11? 11 o'clock in the morning, omega will be taken as minus 15 degree. At 10 o'clock in the morning, omega will be minus 30, and so on in the morning. And in the evening, at 1300 hours, at 1 p.m., this omega will be plus 15. Similarly, at 1400 hours, this omega will be 30 degree, because with every 1 hour, the change is 15 degree. What about 1430? At 2:30 p.m., 1430, omega will be 30 plus 7.5. Right, so it will be 37.5 at 1430, and so on. So the afternoon are taken as positive, morning hours are taken as negative. That is um, our angle, right? Okay, so that's what I have explained. So we can calculate this omega using this simple equation: plus 0.25 multiplied by number of minutes from the local solar noon. For example, I want to find out the solar angle at 11:45. Right, 11:45 means in the before noon, right? So you can use this one. Before noon, we said that will be taken as negative, so that will be 0.25 multiplied by, now for 11:45, it means it is 15 minutes from local solar noon. So that will give us the hour angle. That will be minus 3.75 degree. So instead of memorizing that 15 degree per hour change, we can simply use this equation. If we know the number of minutes away from the solar moon in the morning or in the evening hours, so we can use simply this equation. Okay. So here again in this figure, you see variation of this hour angle. So at noon is 0. In afternoon, it's changing 15, 30, and so on as the sun is going from east to west. It's east, west, north, south axis. So that is the morning hours: 7 o'clock a.m., 8 o'clock, 9, and so on. So it becomes 0 here. Okay, so now we have discussed latitude, and also we have discussed now hour angle. Now we already know about the third basic angle, which is declination. So now we will define this declination angle Here also on this side. So that is next basic solar angle, which is called declination. So how this declination angle is defined here, this del, which will be same as this one, the earth tilt. So it is an angle joining the line, the same OO dash, the line joining the earth center and sun center, and its projection, this line OO dash, its projection on the equatorial plane, that is OB, right? So the angle between OO dash and OB is called declination angle, and that tilt will be maximum on June or December, right? So between June and December, this declination angle will be changing. So as we discussed in the last lecture, so that will be 23.4, that will also be 23.4 degree, and in between it will be 0 for June. We take it as positive. For December, we take it as negative. In between there will be 0 between June and December. That 0 will occur in September. Similarly, after December, again it will start to increase, and in between there will be March, when it will become again 0, and then it will become again 23.4 in June, right? That is this angle, declination angle. The earth tilt with respect to sun, right? Okay, that's what we discussed already. So here is one equation to calculate this declination angle on any day of the year, because as the sun is rotating around, sorry, the earth is rotating around sun, and this tilt is changing. And how it is changing? It is changing with respect to nth day of the year. So if you put any nth day of the year in this equation, we can find out declination, right? And we have another equation to find out the same declination angle, more complicated, but maybe a little more accurate. Here we again have this B, which is given by this equation. Okay. So that is also shown here on 21st of March. The tilt of the earth with respect to sun is 0. 21st June maximum. 21st September, again 0 becomes 0. The earth tilt is still there, but the earth tilt with respect to sun is negligible, is 0. And that is 21 December on the other side. Okay. So here is a summary of that declination angle on different days of the year. June 22, May 21, and July 24 are similar. All right, that is the declination for May 21. Similarly, May 1, April 3, March 21, it becomes 0. Again, it starts to change, but now in the negative direction from March till December. Okay. So the correct way to see this thing, June to July, July to August, September, October, November, December. Right. Then December to January, February, March, April, May, June. That's how this is shown. Okay. Anyways, we have this equation, this one or this one. Just put the nth day of the year and find out the declination angle. Yeah. So now we have discussed three basic solar angles. Now there is a concept of solar time, which we should discuss. Solar time is the time which we use in all these sun angle relationships. The solar time and the local clock time may not be exactly same. The local time, for example, in Bahrain and Riyadh is exactly same, but their longitude is not exactly same, right? That's why the location of the sun at a particular time in Bahrain and Riyadh will not be exactly same because their longitude is a little different. So that difference will give you a different, the difference between solar time, the local solar time, and the local clock time. So both have the same clock time, but both will have a different solar time. The location of the sun will not be same. For example, here on this figure, you see this is the longitude lines, these blue ones, and red ones are also longitudinal lines in this direction, and this is in this direction towards the east, and that is towards the west. So normally in this region, we use the same clock time, but in this entire region, the solar time will not be same. Solar time will be different. So this difference between solar time and local time, we should be taken care of, because this omega, which we just discussed as solar angle, that is based on solar time. That is not based on local clock time. Local clock time. That is not based on local clock time. That is mainly based on solar time. So we should correct the local clock time to solar time, right? For example, now it's 11:45 local clock time in Bahrain. But we need to check whether the solar time is also 11:45, because I want to find out this omega to be used in solar calculations. So that should be referring to the solar time, not clock time. Okay, so I should check what is the difference between the local clock time and the local solar time. Right. So that difference is taken care of by defining an equation, which we will see in this equation, in this part, right? All right, so as we discussed that there is a need to convert the standard time to solar time. By now there are two corrections which we have to apply. One correction which I discussed, that the longitudinal longitude correction, right? If observer is here, right, and this is a line which is passing through the observer plane, right, on which the local standard time is based, right? So there is a correction required for difference in longitude. But because at this point and at this point, we are using the same clock time in this entire region, clock time is same, right? But actually the longitude is not same. From here till here, longitude is changing, but clock time is same in this region. So this is correction one, right? This is a constant correction for the difference in longitude between the observer's meridian, means where the observer is standing, and the meridian on which the local standard time is based. The local standard time is based on this. So we will say +1 hour here and -1 hour here. All right. So in this entire region, we are using one particular time, but actually the longitude is different. Okay. So this is one correction. And to account for this correction, here is one factor which we will study, because sun takes about 4 minutes to traverse 1 degree of longitude. So this longitude changes by 1 degree uh, in 4 minutes. right? And here is that equation, sun, that is called equation of time, to account for this correction, right? So how to use it, just we will see in a moment. So here is that equation in minutes to correct this difference. Second, correction is from the equation of time. I think there is a little mistake probably. Okay, let me check. Let's move on. So the second correction is equation of time, because Earth rotation around the sun, for example, this is Earth rotation, is not circular. That path is elliptical. So it means the Earth will orbit a bit faster when it is closer to the sun, and slower when it will be away from the sun. So it will be a little faster when it will be closer to sun, and slower when it is away from the sun, because this path is not exactly circular, right? So that is one thing which is taken into account. And second is more complex, because the Earth is tilted, is rotating in a tilted plane, right? So this complex geometry will causes the horizontal motion of the sun to vary throughout the year. So we have to combine these things, and these two effects, and we define that equation of time. So what is that equation of time? That is one equation which is given by that Spencer. Yeah. I think we can use either this or this. So this is just a repetition if we want to use it as sine, or if we want to use it in terms of cos. So either we use this equation or this equation. Okay. So the location of this equation is wrong. It should have been placed here as a second option. Okay, that was the confusion. Okay. So this equation has nothing to do with this first comment about this longitudinal change between observer and the local time, okay, local standard time. So we have this equation of time to consider this second effect, right? All those perturbations in the Earth's rate of rotation. Okay. So here, what is n? N is again depending upon nth day of the year. Okay, n is the nth day of the year, which we put it here to find out equation of time. Okay, so let's combine these two factors into one equation. That is important. So for example, I want to find out local solar time, and I know what is local standard time. Then I have to include this equation of time effect here, equation of time from the previous equation which we saw, and here is the factor which will correct for the change in longitude. All right, that is the local longitude where the observer is, and the local standard meridian. Like, what is the local standard meridian? That is 15 degree multiplied by delta T GMT. For example, what is the time difference of Bahrain from Greenwich is about 3 hours. So 3 multiplied by 15. That is the local standard time is based on this thing. But local longitude is not exactly 45. That is different. So that is the local longitude, actual longitude If it is also 45, then this is 0. Okay, then it's fine. There is no need for this correction. But if it is not exactly 45, so whatever is the difference, that is taken care of in this equation. So that is the longitude difference effect, and that is the other factors due to that elliptical path of rotation of Earth around the Sun. And also the Sun itself is not exactly sphere, it also has some elliptical shape, and that is taken care of in this term. So we have to apply these two corrections: equation of time, first correction, second is longitudinal longitude correction. These two will be applied to find out local solar time based on local standard time, right? So we will solve one question, and this will be clear to you. So all these terms I have explained. This longitude is positive if the location is on the east of local standard meridian. Local standard meridian means this Greenwich location. For example, Bahrain is on the east of Greenwich, so we will be using positive here. If the location is on the west of Greenwich local standard meridian, then the longitude will be taken as negative here. So we'll assume here, we'll take negative here. Okay, so this will be clear if we solve few. There are two questions which can be solved. I have here we have a solution for this one. This one you can solve by yourself. So here is the solution. At Islamabad, what is solar time corresponding to 10:30 a.m. Central Time on February 3. Right. So at this location, I want to find out what is solar time when the local standard time, that is local standard time on February 3. It means nth day of the year is known, right? So that will be February 3 means 31 days of January plus 3 days of February. So n is 34. So the equation of local solar time is given here. Now let's find out each term. For example, this longitude of Islamabad, you can see from the Google what is longitude of any location. So that is the exact longitude, 73.1667. But what is the local standard meridian? I told you that is given by 15 degree multiplied by delta T GMT, the time difference with the Greenwich. So 15 degree, and the time difference between Islamabad and Greenwich is 5 hours, so that is 75. So here you see a difference. Local longitude is 73, but the local standard time is based on 75. So there is this difference which has to be taken into account here. Islamabad is also east of Greenwich, so that's why we'll take the positive value here. Now we need to find out equation of time. For equation of time, we saw two equations. One was based on sine function, the other was based on cos function. So let's use this equation. Here, n is related to the nth day of the year. Okay. So find out n first, capital N. Here is the equation. All these equations will be given to you. So here is the nth day. Just put the nth day, which is 34. Put this n here. Just put values and find out the answer. So that is the equation of time. The answer will be in minutes. The unit of this is minutes. So it comes out to be minus 13.35 minutes. Now we have equation of time. We have LON, LSM. Local standard time is given 10:30 am. Just put it in that main equation. So put everything in this main equation. So here is local standard time, 10:30. Equation of time, which we estimated, minus 13. So you have to put minus here, minus 13.35. East of Greenwich, so that's why plus 4 into, because 1 degree change in longitude corresponds to 4 minutes. In 4 minutes, the change in longitude angle is 4 minutes, or in 4 minutes, the change in longitude is 1 degree. Okay, so that is the local longitude, and that is the local standard meridian. Okay, so now first calculate this part. Whatever answer we will get for this part, we will add it to this local standard time. Okay, so this comes out to be minus, this answer of this is minus 20.68 minutes. So the local standard time is 10:30, so you have to subtract 20.68. So so this will be 10 minus 20.68. So 0.68, so it is about 10 hours and 9 minutes. 9 minutes, 9.32 minutes, right? So the answer is the local solar time is 10:09. So if you round it off, this 21.68, you can say it is 21 minute. So 21 minutes you have to subtract from this minute part, which is 30. Okay, so the local solar time is 10:09, but local standard or standard clock time is 10:30. So our angle, which we discussed before, that should be based on this local solar time, not on the basis of local standard time. But for simplification, because the difference is normally not very large, so you may use the local standard time for simplification, but the correct or more accurate way is to use local solar time to find out that omega. Those basic solar angles which we studied, phi, latitude, declination, and hour angle. So the hour angle should be based on local solar time, which is this one, right? Which we have calculated using that equation from the local standard time.